Solve x minus 1 over x plus 2 is greater than 3. To solve this type of inequality, these rational inequalities, we're first of all going to rearrange them so that they're greater than or less than or equal to 0. I'm going to have x minus 1 over x plus 2 minus 3 is greater than 0. I'm going to then combine these algebraic fractions to x minus 1 over x plus 2, take away 3 lots of x plus 2 over x plus 2 to get a common denominator so I can add them, which means I'm dealing with x minus 3x, so that's minus 2x, minus 1 minus 6, so minus 7, all over x plus 2 is greater than 0. Actually, instead of solving this inequality, I'm going to solve this inequality, which is algebraically identical. Now, if this rational function is bigger than 0, there are two possible cases. The two cases I need to consider are, I'll split them up, either minus 2x minus 7 is bigger than 0 and x plus 2 is bigger than 0, or the other case is minus 2x minus 7 is less than 0 and x plus 2 is less than 0. That is, for this fraction to be positive, either the top and the bottom are both positive, or the top and the bottom are both negative. So let's look at the case where they're both positive to start with. Solving these inequalities, I'm going to get, on this first one, I'm going to get adding the 2x to both sides. So I get 2x is less than minus 7. And that is going to be, so x is less than minus 7. And, so that's the first inequality, x is less than negative 2. Oh, sorry, it's not minus 7, that's minus 7 over 2. So x is less than minus, sorry, that's not less than, that's greater than. This is greater than 0. X is less than minus 7 over 2, and x is greater than minus 2. Now, if we think about this on the number line, minus 7 over 2 is minus 3.5, minus 2. We need it to be both less than that and greater than that. So this is not possible. There's no solutions to this inequality with that being true. So now let's look at the other one. First of all, add the 2x. So we get 2x is greater than minus 7 this time, which gives me x is greater than minus 7 over 2. And this time I've got x is less than minus 2. So x is greater than minus 7 over 2 and less than minus 2. Now, if we go back to our number line, that's this bit here. Now, that can be true. So, in fact, this one does work. It is true when x is greater than minus 7 over 2, but less than minus 2. And this is the solution to this inequality, the only possible set of solutions. Let's have a look at this one graphically to see what's going on. If I draw my initial function, this is x minus 1 over x plus 2. Notice that I've got a horizontal asymptote here at y equals 1, and I've got a vertical asymptote here at x equals minus 2. When is this greater than 3? So if I draw in the line y equals 3, when is this graph greater than 3? That's this bit here. Now, we can see that this point is at minus 3.5. That was at minus 7 over 2 that we found. So its a value is greater than that. But then it stops when we get to this vertical asymptote. We're not looking for another critical point here. We've got a vertical asymptote that stops it from working at this stage. So it is from minus 3.5 up to the vertical asymptote, which is at minus 2. Another way to consider this is to think about the graph of the transformed function, which was minus 2x minus 7 over x plus 2. And when is this positive? When is this greater than 0? So when is this greater than 0? We look for the root, which is at minus 3.5. And again, in a very similar way, it is positive for this bit of the graph, which is everything bigger than minus 3.5, but has to be less than this asymptote at negative 2. Because once we go past that asymptote, we end up being negative again. So graphically, we have two approaches. We can either algebraically manipulate and look for the roots, or probably easier if we've got our calculator is just to draw the two graphs and find the point of intersection. But don't forget that asymptotes come into play when we're dealing with rational functions.